first example problem, we are told we have vector k. Vector k, where vector k is designated by having an arrow for a hat, has magnitude lowercase k without a hat, and is oriented at an angle theta above the positive x-axis. We're assuming that vector k is oriented in the first quadrant. The angle is between 0 and 90 degrees. So let's draw that picture out. So here are my x and my y axes. So here is the positive x-axis. Here is the positive y-axis. Now, whenever you say positive x-axis or negative x-axis, basically positive x-axis will point in the direction of increasing x. Negative x-axis will point in the direction of decreasing x. So sometimes we just say x and y axes. You assume that they mean the positive x and the positive y axis. Now, vector k has a magnitude k, so that means vector k has a magnitude. When I draw that vector k on the board, I will draw it a certain length, and it has a certain angle that it is oriented above the positive x-axis, and that angle is theta. So that means that when I drew this picture, vector k from here to here has a magnitude of k, or an amount k. This is vector k. Now, vector k also has projections onto the x and y axes. So think about what it means. Think about what do we mean by a projection? If you imagine there is a very bright light bulb really far up near the ceiling, shining straight down on this vector, how much of the x-axis would be covered by this vector? So we have a really bright light bulb 100 miles above here. And the light bulb is shining down. And when the light bulb shines down, this much of vector k will cover the x-axis. So this much of the x-axis is going to be in the shadow of vector k. So if this is the shadow of vector k from here to here, this is the projection of k onto the x-axis. I will call this kx. I could also refer to this as the component of the x component of k, or the horizontal component of k. If I am beginning here and I want to get to the tip of vector k, and I ask how far overall to the right did I have to walk, I would have walked this far to the right. It is also true I would have had to walk somewhat upward as well to end up at the tip, but we did not ask that. We only asked how far to the right will I have moved when I got from here to here. That is the same as this projection of k onto the x-axis. Simultaneously, I could say, let us pretend 100 miles way over there, there is a bright light bulb shining, and when that bright light bulb shines, some of that light will hit this vector k, casting part of the y-axis in shadow. How much of the y-axis is going to be covered in k's shadow? So we have a light bulb really over there, we have light coming in, and then it hits vector k, and this vector k is going to be projected onto the y-axis by this amount. So this much of the y-axis is going to be covered by the shadow of this vector k. So I could call this amount ky. Now, if you look at this picture, you could also ask equivalently, if I walked from the very beginning of vector k to the very end of vector k, how far upward would I have walked? Well, you have walked from here to here. The amount upward you would have walked would have been from here to here as well. I am not asking how far to the right did I walk. It is true, I did walk to the right when I went from here to here, But the question we are addressing at the moment is only how far upward did I walk? And it would be from here to here. So from here to here. So I could also call that the y component of k, or the vertical component of k, since we're assuming y is the vertical axis, or the projection of k onto the y-axis. I could think of all of those as being the same thing. Now, if I look at this picture, I notice kx is this amount. If I bring it up, this is also going to be kx. So this distance here is also kx. And this distance here is also ky. So the reason I'm pointing out several different pieces of locations where you could find the components of this vector k is sometimes, depending on what is given in a problem, it might be easier to find your ky here or your kx up here. Usually you would find it just projected onto the axis itself, but not 100% of the time. So I just wanted to take a moment to point that out. And again, this total from here to here is the magnitude of k. So it's I could visualize it by asking, how long of a line do I need to draw onto my paper? Now, vectors are not always measured in length, so vectors do not always represent lengths. Vectors could represent how hard of a push. And how hard of a push, you don't measure how hard you push in meters, you measure it in different units. But for a mental visual picture in your mind, you can think of how long is this going to be when I draw it on paper, how long is this going to be when I draw on paper, and so on. Now, looking at this picture, I immediately am seeing lots of right triangles. I have one right triangle over here, and this is going to be the right triangle that I focus on for this example. So if I say here is my x and my y axis again, and here is my vector k, and here is this angle theta. Well, the vertical part of this vector is ky, and the horizontal part of this vector is kx. And here is a right angle. So if I look at this and see a right angle and a right triangle, I could then say, well, the sine of theta is going to be opposite over adjacent. So sine is always defined as opposite over hypotenuse. The hypotenuse has a magnitude k. K is the vector itself with direction specified. K without the arrow designated vector just means the magnitude of k, or the amount. So in this case, the side opposite theta is ky, and the hypotenuse is just k. And I could similarly say cosine of theta is going to be adjacent over hypotenuse. Adjacent here, the side next to angle theta is kx. And the side that is the hypotenuse is just k by itself. Now, very often we will want to know what ky and kx are. So if I say this equation implies sine theta equals k y over k, then I get ky is equal to k sine theta, and cos theta equals kx over k, and then that means kx, based on how I drew this picture, is equal to k cos theta. Especially, somewhat when we work with vectors, but especially when we work with forces, we are very often going to be using ideas like this a lot. It won't be 100% of the time, but as I said, we are going to use these ideas a lot. Now, what about the scenario where, let's look at a scenario where our angle is measured coming from the y-axis instead of from the x-axis. And let's see how that changes things. And in this scenario, in the second example problem, we're actually going to put numbers in. So in the second example problem, we are told we have a vector that I'm just calling S. Vector S has a magnitude of 4 and it's directed at an angle 15 degrees to the right of the positive y-axis. So I have drawn my x and my y-axis, and we are told that vector S has a magnitude of 4 and it is shifted 15 degrees to the right of the positive y-axis. So here is the positive y-axis pointing upward, and vector S has a magnitude of 4, but vector S is shifted a little bit over. From here to here is 90 degrees, so 15 degrees is 1/6 of the way over, 1/6 of 90. So vector S will look something like this. So here is my vector S. This is a 15-degree angle, so 15 degrees. Now we are trying to find what is the x component and what is the y component. What are the horizontal and vertical components of this vector S? We're told vector S has a magnitude of 4 that I'm going to write up here just so it kind of stays out of the way. And what I'm going to do is, this is like asking, what is the projection of S down onto the x-axis? That is my Sx. What is the projection of S onto the y-axis? That is my Sy. So if I were to go straight down, I could say this is Sx, and if I were to go across to the y-axis, this here is Sy. Now, if I look at how I drew this picture, I notice I drew a rectangle. And so if this is Sy, this also will be Sy. And if this is Sx, this also will be Sx. Because opposite sides of a rectangle will have the same length. At this point, I'm going to say this picture is kind of busy, so I'm going to redraw the picture on the other side of the board just to clean it up, make it a little bit neater. So let us say here is that same triangle I drew. Here is my right angle. This side has a magnitude of 4. This side is my Sx. This side is my Sy. We are also told this angle is 15 degrees. Now, at this point, I am going to remember that sine, cosine, tangent are defined as being in relation to the angle you're talking about. The angle I'm talking about here is 15 degrees. So here, opposite 15 is Sx, and adjacent or next to 15 is Sy. So I could say cosine of 15 is equal to adjacent over hypotenuse, so that would be Sy over 4. And if I do some algebra then, I get 4 cosine 15 is equal to Sy, and I get Sy is equal to 3.86. Similarly, I could say sine of 15 is equal to Sx over 4, because Sx is the opposite. And so I get 4 sine 15 equals Sx, and so I find the x component of vector S, or the projection of vector S onto the x-axis, or the horizontal component of vector S, is going to be 1.04. So at this point, I found the components of vector S. Now, as in many problems we encounter in this course, there may be more than one way, one method to solve it. So here's another way I could think about this problem. let's go back to this picture here, and I am going to erase this stuff. So at this point, as I said, as far as I'm concerned, you're done with the problem. You get 100%, you're great. But maybe you want to solve it a different way. We know that a right angle is 90 degrees. And so if this angle is 15 degrees, that means this angle here must be 75 degrees. So I just as well could have said, let's draw this triangle now. Let's draw this triangle over to the side and look at that. So if I were to draw a triangle where the hypotenuse is 4, this angle over here is 75 degrees. And now this is SX and this is SY. Here's my right angle. At this point, based on how I drew this picture, this side is opposite 75 degrees. This side is adjacent to 75 degrees. Notice opposite and adjacent now adjacent is my X and opposite is my Y. When we were considering 15 degrees, it was reversed. So I could say cosine of 75 is equal to Sx over 4, and I then get Sx is equal to 4 cos 75, and I still get 1.04. And if you do the same thing for Sy, I'll leave it to do in your notes, you would also get, by the same method, Sy is equal to 3.86. So the take-home message here is when you're working with sine, cosine, tangent, the numbers that you enter are very often the numbers you enter. X will be affiliated with cosine, Y will be affiliated with sine, but that's not guaranteed to always be the case. And when we consider this 15-degree angle here, that was a counterexample where it is not the case. So in the next problem, we are going to look at how do you treat vectors that are not pointing in the first quadrant? How do you treat vectors in the second, third, or fourth quadrant?